We can also look at things happening at constant pressure. This is a very common situation. When we have a chemical reaction occurring in a container that's open to the atmosphere, the pressure is going to be constant. We don't have a constant volume now, so we can have energy evolving as both heat and as work. Usually, we're only interested in the heat exchanged and not in the work, because the work actually isn't very useful at all. So the enthalpy, which is given the symbol capital H, the enthalpy is the sum of the internal energy and the product of the pressure and volume for that system. So no deltas yet. H equals E plus PV. So enthalpy is a state function, like the internal energy was, like pressure and volume. It only matters where you started, where you end up, how you get in between has no effect on it. So we look at enthalpy change, that's delta H. The enthalpy change for a reaction is the heat evolved at constant pressure. So we had H equals E plus PV. So then delta H is delta E plus P delta V. Well, delta E, we said, was Q plus W, right? The change in internal energy is the heat plus the work. So that's Q plus W. And what does W equal? Negative P delta V, right? This isn't constant volume. The volume's allowed to change. So pressure volume work, W is minus P delta V, or we could say that negative W is equal to P delta V. So we've got P delta V here. That's equal to negative W. So we've got negative W, and then we had QP plus W. QP plus W minus W, the W's go away. It's not an accident. They did that on purpose. The result is that delta H equals QP. So the enthalpy change equals the heat exchanged at constant pressure. So delta E and delta H can be very confusing because they are so similar and yet they are different, but the difference is very subtle. And at this level, general chemistry, we can mostly ignore the differences between them. But let's just go over it so that at least we've heard of it. So delta E is the change in internal energy. That measures all the energy that's exchanged with the surroundings, the heat and the work. Delta H, the change in enthalpy, measures only the heat exchanged under constant pressure. So constant pressure is very easy to achieve. You just have it open to the atmosphere, and the pressure is always roughly 1 atmosphere. So many times these numbers are very close to the same number. The difference is largest when you have reactions that produce or use large quantities of gas, where you have large volume changes, because then the work is a little bit more important in terms of the overall energy changes when you have a big delta V. But we don't have to worry about that. The signs of delta H and delta E follow the same conventions. So again, think about money going into and out of your wallet or your checking account. Why do we call it a checking account? Does anybody use checks anymore? Not much. What are we going to call it when nobody uses checks? I don't know either. But think about money going in and out, right? So the sign is the same here. Delta H is positive when heat's being absorbed by the system, money coming in to your account. This is called an endothermic. Endo is a prefix meaning into. And thermic refers to heat. So into heat, or heat into you, right? And endothermic. When delta H is negative, heat's being released. Heat's going out, money going out is a debit on your account. And that's called an exothermic reaction because exo, like exit, that's where you go out. We mentioned hand warmers at the beginning of this chapter. Those chemical heat packs contain iron filings that get oxidized, and that's an exothermic reaction. It releases heat. Your hands are the surroundings, and so the heat goes into your hand and warms up your hands. There are also chemical cold packs. Ammonium nitrate is a common ingredient in this. When ammonium nitrate dissolves in water, it's an endothermic process. It absorbs energy from the surroundings. So your hands get cold because the chemical reaction is absorbing heat from them. And here we have a picture of a flame. This is an exothermic reaction. The chemical reaction of combustion occurring here releases a lot of energy into the surroundings, and we feel that as heat. So identify each process as endothermic or exothermic and indicate the sign of delta H. Okay, so an ice cube melting. Endothermic or exothermic? Exothermic? Yeah, it's like, So these are not always as easy as we maybe think they should be. So ice cube melting, one of the things you can help do or think about to help yourself is like, well, how would I make an ice cube melt faster? Put heat on it, right? Stick it on a frying pan on a hot burner, it'll melt really fast. Why? Because we're putting lots of heat into it. It's endothermic. So an ice cube melting is endothermic. And for an endothermic reaction, what's the sign on delta H? It's positive. It's greater than 0. Because heat's going into the system, money's going into your wallet. Nail polish remover quickly evaporating after it's accidentally spilled on the skin. What does that feel like? Feels cold, right? It's the same as getting this acetone on your skin. It feels cold. Alcohol, similar. Why does it feel cold? It's evaporating. So is evaporating endothermic or exothermic? How would you make it go faster? Heat it up, right? If you add heat to it, it goes more. So it's endothermic.
Basically, it's receiving the heat given off from your skin.
Yes, it's taking heat from your skin. What makes this tricky is it really depends on how you define system and surroundings, right? If you're describing your skin as the system, your skin is losing heat, so that would be exothermic. But we're talking about the nail polish remover. It's evaporating, it's taking the heat. So this is also endothermic. And the sign for delta H will be positive because all endothermic processes have positive delta H. Gas burning within the cylinder of an automobile engine. Exothermic. Anything burning, right? Think of a match and stick your finger close to it, burning, ouch, right? It's giving off a lot of heat. Exothermic. And if it's exothermic, what's the sign of delta H? It's negative. So we say delta H is less than 0. Any questions? Yes?
So, like, if you put the ice on the refrigerator, so it didn't get colder, is it okay?
If you put ice on what?
On the refrigerator.
I'm sorry,
Refrigerator.
on the refrigerator. So if you put ice in the refrigerator and the ice gets colder, is that what you're talking about? Yeah, so that would be exothermic because the ice is losing heat. So did you know that when an ice cube freezes, it gives off heat? No, that seems weird, doesn't it? Well, an ice cube melting is endothermic, right? That makes sense to us. If you wanted to heat it up, if you heated it up more, I'm forgetting how to talk. If you want the ice cube to melt faster, put it on the stove, turn the burner on, right? It'll melt much faster. So ice melting is endothermic. Then the opposite, water freezing, is exothermic. It's weird. It's like, well, how could that be? Well, ice doesn't form spontaneously at room temperature, does it? How do you make ice? You stick it in the freezer. You stick water in the freezer. What's the freezer do? The freezer is pumping heat energy out of the inside of that box. Where's the heat energy coming from? It's coming from the water. Now, it makes sense that the water was at room temperature, and so we have to take heat out of it to cool it down and get it to the freezing point. But at freezing, it's still releasing energy as it freezes. We'll talk more about that later, but that principle is what saves the oranges and lemons and grapefruits near Reedley in the winter when it starts to freeze. They flood the fields, and water freezing releases heat and moderates the temperature. It's crazy. Yeah, it's very neat.
Rather than having dry dirt.
Yeah, instead of having dry dirt,
Kill the plant. Instead of having dry dirt, make it kill the plant. Yep.
well, actually, it's not that the frost kills the plant. It's that the oranges freeze. The trees, for the most part, are going to be okay, but the oranges freeze at about 26 degrees Fahrenheit, and then they're worthless.
That's how you kill water.
Yeah, so put water in the field, and as the water freezes, it releases energy and keeps the air and everything around it at 32 degrees Fahrenheit. And that temperature there won't drop below 32 until all the water has frozen. So as long as there's liquid water, you've got relatively warm air there. Yes?
Can that be applied to guava also?
To what?
Guavas?
Guavas? Yeah, it would work with anything.
I just asked because I haven't that one.
Yeah. So the reason that and we'll talk more about this later also, the oranges freeze around 26 because they've got sugar and other things dissolved in the water inside of them. If you just had, balloons full of water on the tree instead of oranges, they'd start freezing at 32. And so because water freezes at a higher temperature, it can be used to moderate the temperature in the orchard.
Sugar that's inside.
It's the sugar in the oranges that...
That's a buffer.
It's a colligative property that any dissolved solid will cause the freezing point to be lower and the boiling point to be higher.
This sugar kind of has similar properties to water.
No, the thing is the sugar molecules get in the way of the water freezing. That's one way to think about it. They disrupt the freezing of the water, and so the water molecules have to get even slower before they can form their solid crystals. So sugar, salt, it doesn't matter what it is, just anything dissolved. Okay, so let's talk about this. Let's get back on topic. Molecular view of exothermic reactions. So exothermic reaction gives off heat, causing the temperature of the surroundings to go up. Where does that energy come from? It comes from energy that was stored within the chemicals. Stored chemical potential energy. No, it's a form of potential energy. And when those reactants react, that energy is released as heat. So when things react, existing bonds are broken and new bonds form. So we've got existing bonds being broken, new bonds are made. The products of an exothermic reaction have lower chemical potential energy than the reactants did. So gasoline has high chemical potential energy. After it burns, the products have low chemical potential energy. The energy that was stored in the bonds is released. The opposite is true for endothermic reactions. So here, the temperature of the surroundings drops because the reaction is pulling heat energy out of the surroundings. Again, we've got existing bonds being broken and new bonds being made, but now the bonds in the products have more energy than the bonds in the reactants did. So it's taking that thermal energy and storing it in the molecules. Yeah, loud people in the hallway. So enthalpy of reaction. So delta H RXN, this is the change in enthalpy for the reaction. We call it the enthalpy of reaction or the heat of reaction. So heat and H kind of makes sense, right? This does equal the heat absorbed or evolved under most circumstances. But the heat is an extensive property, meaning it depends on how much of the sample you have, right? So if you think about burning a teaspoon of gasoline versus burning a gallon of gasoline, is there going to be a difference in the amount of energy that's released? Yeah, right? Because if you burn a little bit, you get a little bit of energy. If you burn a lot, you get a lot of energy. So the delta H is specific to the amount of stuff, right? We saw that in that problem we just did. So by convention, just because everybody agreed to do it this way, when we write a chemical reaction and we tell what the heat of reaction is, this number relates to the molar amounts in the balanced chemical equation. So this 2,044 kilojoules of energy being released is for 1 mole of propane being burned, for 5 moles of oxygen, for 3 moles of CO2 being produced, for 4 moles of water being produced. Okay, so this amount is for the balanced chemical equation, however it's written, the coefficients are the number of moles. So ammonia reacts with oxygen according to this equation, and we've got delta H. Calculate the heat in kilojoules associated with the complete reaction, of 155 grams of ammonia. So this heat of reaction is telling us that 906 kilojoules are released, the negative sign, when 4 moles of ammonia react. We could also relate it to 5 moles of oxygen, 4 moles of nitrogen monoxide, 6 moles of water, but we're not interested in those other ones. We're just interested in the ammonia. So 155 grams of ammonia. What I want to do is I want to convert that into moles because this relates to a molar amount. So what I'm doing here is I'm going from grams of ammonia to moles of ammonia to kilojoules. I don't have to go moles of this to moles of that because I can go from any one of these directly to the energy. So 155 grams of NH3 multiply, on top is moles of ammonia, on the bottom is grams of ammonia. So I want those grams to cancel out. And then over here, I've got kilojoules on top and moles of ammonia on the bottom. So moles of ammonia cancel out. So Delta H is minus 906 kilojoules. So minus 906 kilojoules for 4 moles of ammonia. And then I need the molar mass of ammonia, and just to speed things up, it's 17.034. So we've got 155 divided by 17.034 times negative 906 divided by 4. So this is minus 2061.025, it's a decimal point, kilojoules. And we're looking at sig figs, and we've got 3 here and 3 there, so we should round this to 3. Again, rounding in the tens place, be careful. 2,000 and 200 are not the same. So this would be negative 2,060 kilojoules. The negative sign tells me that that energy is being released. So in the question here, or the statement, it says calculate the heat associated with. Associated with doesn't mention a direction. So then if there's a negative, I need to include the negative. If this was calculate the heat released by the complete reaction, then I would just say 2060. Because if you ask me how much did you pay for that double gulp? Minus 99 cents. No, I asked how much you paid. Oh, I paid 99 cents, right? So paid tells the direction. Question?
I was going to ask, where do you get the ratio of the moles to kilojoules?
Good question. Where did I get this? So because everybody agreed to do it this way, this amount of energy is related to 4 moles of this. So the 4 comes from the coefficient. So we can just insert mole between the number and the chemical formula. So if 4 moles of ammonia react completely, meaning there's enough oxygen for it, this much stuff is going to be produced, this much energy is going to happen. Does that make sense?
Yeah, I thought it was like for NH3, just like in general, not.
No, it's for this particular reaction. Yeah.
That makes sense.
And that would apply to if it was 5 moles of oxygen?
Yeah, so if it said, well, you know, what about the complete reaction of 155 grams of oxygen? Well, I would take grams of oxygen, convert it to moles of oxygen, and then this here would be minus 906 kilojoules per 5 moles of oxygen, because there's a 5 in the balanced chemical equation. So we don't have per mole or anything. We just have this delta H with a chemical reaction, chemical equation.